The next section of trigonometric equations that we're going to look at are those that are quadratic in form. Some trigonometric equations are in the form of a quadratic equation, meaning they're of the form au squared plus bu plus c equals to 0, where u is a trigonometric function and a is different from 0. For example, what you're kind of looking for in this setup is where you have one particular trig function, and in one instance it should be being raised to the first power, and in another instance to be being raised to the second power, kind of like what we see here. If I look at this first equation, 2 cosine squared x plus cosine x minus 1 equals to 0, this is an equation, it's a quadratic equation, not in just the simple variable x, but in the variable cosine of x. If we were to do a substitution on this, you could let u be equal to the cosine of x, and under this substitution, this would reduce to the simple quadratic in the variable u, 2u squared plus u minus 1 equals to 0. We could solve this quadratic equation for the variable u. Mostly in this section, they should be factorable, or potentially might need to use the quadratic formula on occasion. And then once you find the values for u, you can back substitute to solve for the values of x by setting u equal to cosine of x. If you feel very comfortable with your factoring methods, you don't necessarily need to do the substitution, but if you like it and if it helps, you're more than welcome to. I'll do it for the first example, and then maybe I'll just skip it and factor the next one without doing the u sub. In example 4, we want to solve the equation 2 cosine squared x plus cosine x minus 1 is equal to 0, and we want to find the solutions for this one that are between 0 to 2 pi. So we look at it, it definitely has two instances of the cosine, and we do notice that it's kind of that pattern, it's quadratic in form, because we have one term that's cosine squared, another that's cosine to the first power. So let's do a substitution on this. Let's let u be equal to the cosine of x. Under this substitution, our quadratic equation becomes 2u squared plus u minus 1 equals to 0. You can solve that quadratic using whatever method you're comfortable with. There's many ways to solve a quadratic equation. This one should factor. It's going to factor as 2u and u. We're going to have a 1 and a 1. And then the sign should look like this. It's going to be a plus and a minus. If you're uncertain or if you don't feel comfortable, you can always expand it back out, distribute it, but that will be the factorization for 2u squared plus u minus 1. We now go ahead and set each factor equal to 0 individually. So 2u minus 1 equals to 0, and u plus 1 equals to 0. For the first part, we would add 1 and then divide by 2. That will give us u equals to 1/2. And then the second part would u give us equals to negative 1. So we now have solved for the u values. We know u is going to be equal to 1/2, and u is going to be equal to negative 1. And now what we can do is go ahead and back substitute. Everywhere we see the variable u, we can replace it with the cosine of x. So we need the cosine of x to be equal to 1/2, and we need the cosine of x to be equal to negative 1. And for these equations, we're just trying to solve them between 0 and 2 pi. Let's work on the second one first because it might be one of the easier parts. We want the cosine of x to be equal to negative 1. That's going to come from one of our quadrantal angles. The cosine is precisely negative 1 at the angle pi. So this will give us the solution x equals to pi. It's going to be one answer. Let's come over here to the second part. Cosine of x equals to 1/2. Again, if it's helpful, think about all students take calculus. Where between 0 to 2 pi is the cosine positive? Well, that's going to be quadrant 1 and quadrant 4. We should know from our knowledge of the unit circle that the angle in quadrant 1, in which the cosine of x is equal to positive 1/2, that angle should be pi over 3. And the solution in quadrant 4 should be the angle whose first quadrant reference angle is pi over 3, and that's going to be 5 pi over 3. Okay. So altogether, this equation has three solutions. The solutions are pi over 3, pi, and 5 pi over 3. Let's take a look at another one. In example 5, we want to solve the equation 4 sine squared x minus 1 equals to 0 for 0, again, in between 0 and 2 pi. This is another quadratic trigonometric function. It's quadratic in the variable sine of x. If you, again, wanted to do a substitution, you could do that. You could let u be equal to sine of x. But I'm just going to kind of solve it as it is. This would actually factor. It factors as a difference of squares. Or another way you could approach to solving this quadratic is this is one of these quadratics where you can use the square root method because there's no sine of x to the first power term. So let me just go ahead and I'm going to isolate the sine squared function first. I'm going to add 1 to both sides. I can then go ahead and divide both sides by 4. So we would get that the sine squared of x is equal to 1/4. Keep in mind what this notation means. When we say sine squared x, this is really the value of the sine of x squared is equal to 1/4. So to get the sine by itself, we want to get rid of the square. So we're going to do the square root of both sides. Okay. Keeping in mind, whenever you do the square root of a real number, there's two square roots, both the positive and the negative root. So we get the sine of x is going to be equal to plus or minus the square root of 1/4 would be 1/2. So we need to know where is the sine of x going to be equal to 1/2, and also where is the sine of x going to be equal to negative 1/2. And again, we're only looking for the solutions right now between 0 and 2 pi. For the first piece, if we think about our all students take calculus, sine should be positive in quadrant 1 and quadrant 2. The first quadrant angle, where the sine is going to be 1/2, that should be pi over 6. The second quadrant angle should be such that its first quadrant reference angle is pi over 6, and that would be 5 pi over 6. So that's two solutions. Coming over to here, where is the sine of x going to be equal to negative 1/2? Well, from all students take calculus, the sine is going to be negative in quadrant 3 and negative in quadrant 4. Those two angles should have a first quadrant reference angle of pi over 6, because that's where the sine has the value equal to 1/2. The angle we should get in quadrant 3 is going to be 7 pi over 6, and the angle that's going to appear from quadrant 4 would be 11 pi over 6. So this particular equation has four solutions: pi over 6, 5 pi over 6, 7 pi over 6, and also 11 pi over 6. The next set of equations we're going to look at involves separating two different trig functions. It's kind of an extension of the last method we saw, where if you're able to get all of your trig functions to one side and factor, then you can kind of set each factor independently equal to 0, like we're going to see next. In example 6, they want us to solve the equation tangent x sine squared x equals 3 tangent of x, and we're still only looking for solutions between 0 to 2 pi. Well, for this kind of equation, we look at it, there's precisely two terms, one on the left-hand side, one on the right-hand side, and both of those terms have a tangent of x in them. So what we can do is let's try to get one side to 0. Here I'm going to subtract the 3 tangent of x from both sides. And that should produce the following. We're going to have tangent x sine squared x minus 3 tangent of x equals to 0. And now we can pull out the common factor of tangent of x. So we have that the tangent of x times sine squared x minus 3 equals to 0. So we have the left-hand side factored, set equal to 0. We can use the zero product property of the real numbers, which says we can set each factor equal to 0 individually. So we need to solve for where is the tangent of x equal to 0. And where is sine squared of x minus 3 equal to 0? Well, let's take a look at the first one. Tangent of x equals to 0. For the solution between 0 to 2 pi, if it helps, you can think of the tangent as being sine over cosine. So the tangent of x will essentially be equal to 0 whenever the sine of x itself is equal to 0. And that's going to occur at 0 and pi. So we get two solutions from this, x equals to 0, x equals to pi. Notice that they have a strict inequality here. 2 pi would have been another solution, but they say that x has to be strictly less than 2 pi. So from that piece, we get two solutions, 0 and pi. Let's now look at the second piece. We want to isolate the sine. This as a subpiece, is a trigonometric equation in the variable sine of x. We can get the sine squared term by itself by adding 3 to both sides. We can now go ahead and take the square root of both sides. And so we get the sine of x is going to be equal to either plus or minus the square root of 3. So we would need to know, where is the sine of x equal to positive radical 3 at? And where is the sine of x equal to negative radical 3 at? Well, it might look somewhat familiar. I mean, we do have some places on the unit circle where the sine of x is equal to radical 3 over 2, but we've never specifically solved for any place where the sine of x is equal to radical 3, nor negative radical 3, and for good reason. The square root of 3 itself has a value that's approximately 1.7. And we know that that is larger than the amplitude of the sine. The largest value that the sine can take on would be the value positive 1, and the smallest value you can get out of the sine of x would be negative 1. So neither one of these pieces here would have any solution to them coming from these parts here, because the sine of x is never going to be equal to negative radical 3, nor to never be equal to negative radical 3. So all in all, we get two solutions, x equals to 0 and x equals to pi.